Obviously, we haven't talked before. This is a first for us.
Hi.
Hi. You are my husband, Sean Carroll's, one of his many co-bloggers on Cosmic Variance. You want to introduce yourself?
Yes, my name is Julianne Del Canton. I'm a professor of astronomy at University of Washington in Seattle.
Okay. And you blog...
And you're Jennifer.
I'm Jennifer. I'm a science writer, and I blog mostly about physics, certain aspects of other science, and more and more calculus, believe it or not, which we can...
I think that's fabulous that you're going back to the calculus.
It's, sometimes, I tell you, it's probably the biggest strain on our marriage right now is him teaching me calculus, because I get frustrated. And
it's hard to learn things from your spouse sometimes, right?
He's a great teacher. I mean, I'm actually very lucky that he's one of those scientists that has a real gift for communication, because I think I'd stalk someone else. But I was looking over kind of your background and your CV, because this is kind of a getting acquainted conversation for us. Sean's raved about you, and I love your blog post, but we've actually never met. But one of the things I noticed, which I think is totally cool, is you discovered your very own comet.
Yeah, and that was an absolutely spurious event.
Well, kind of aren't they always? I mean, you can't say...
No, there's people who look for them. There are people who... there's amateur comet hunters who systematically scan different parts of the sky every night and look for things that are different.
Oh.
There are large surveys where they take repeated measurements of the sky and look for things that are different. So these are more kind of professional-oriented things, and try to... One of the things... They find many things, including asteroids and variable stars, but another thing that they do find are comets. So there are large numbers of comets that are found in a very systematic fashion, rather than just somebody noticing and saying, "Hey, what's that?"
Right. Now, was yours part of the Sloan Digital Sky Survey?
Yeah. So there's this large project called the Sloan Digital Sky Survey, and it's an absolutely wonderful project that's changed many, many aspects of astronomy. And what the survey does is it takes images of the sky through 5 different filters. So it's basically like putting on a pair of red sunglasses and taking an image of the sky, and then putting on a pair of green sunglasses and taking an image of the sky, putting on a pair of blue sunglasses. And from that, you can kind of build up a multicolored picture of what's going on. Mm-hmm. And the sky is really large. Right? The sky is...
Space is big.
Space is really big. It's not even just the space, it's just the angular scale of the sky. Like when you look up overhead and you think about the fact that a typical telescope point of view is sort of less than your pinky thumbnail, held it. I'm trying to do this so it shows up on the screen. Held at arm's length. If you look at the size of your pinky thumbnail.
See, right there.
Yeah, that's small. That's larger than the typical field of view of a standard astronomical telescope. And so, if you imagine having to tile the whole sky with something that small, you can realize it's a tremendous amount of work, and you have to do a really systematic study. So, this Sloan Digital Sky Survey has been spending many, many years with these beautiful cameras taking these multicolor images of the sky. And it's this wonderful database of information, and it's open to the public. You can go to sdss.org, and you can look at images, you can download images, and so it's fun just from an amateur, interested person perspective, but it's also wonderful from a professional scientist perspective, because it's this rich trove of data. You used to spend a lot of time writing proposals just to get time to look for one night at one specific part of the sky, and instead Sloan's already done it, so you don't need to waste that time trying to get that data, because that library is there and publicly accessible. And they're also taking spectroscopy of a huge number of things that they see in the sky, from which we can learn a lot about the different stars and the galaxies and the distances, and there's just been revolutionary science that's come out of this project. It's a whole new scale of just volume of data quality, so it's a wonderful, wonderful thing. So at the time that the survey first started going, I was doing a lot of work on something called low surface brightness galaxies. And these are galaxies that have very, very low contrast against the night sky. So the night sky, everybody talks about, the inky blackness of the night sky. The night sky is not actually that dark. So during the day, the sun's energy excites various atoms and molecules in the atmosphere. And then after the sun goes down, those molecules fluoresce, and they give off that energy in the form of light. So the sky actually has sort of a faint glow to it. There's also light in the night sky that's what's known as zodiacal light, and that's light from the sun. So even though the sun is set, that light from the sun goes out into the solar system and bounces off all these little dust grains,
right,
and then comes back into your eye. So you can actually see it. You can see the zodiacal light sometimes right in your sunrise, you'll see this big triangle of kind of glowy stuff coming up from the horizon. If you're in a very dark place, you're not going to see this if you're in downtown Los Angeles.
We can't see anything in downtown. We see smog.
No, it's the marine layer.
Okay, yes,
or as
the
a friend of mine
marine
used to call
layer.
it the urine.
I've got to get that lingo down.
Yeah. So anyways, so the night sky is relatively bright. And so in the same way that you can't see stars very well in the daytime, you can't see if somebody shines a flashlight in the daytime, you can't really tell whether it's on or not.
Right.
And it's a problem of contrast. If you're in a dark room and you turn on a flashlight, it's like, it's way too bright.
Right.
So there are kinds of galaxies that have very they're what we call their surface brightness, so basically how much light per unit area on the sky. It's very, 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 very dim.
Okay.
And it's an interesting population because since it's hard to see, lots of people have overlooked it. It's hard to figure out when you're trying to just do a census of how many galaxies there are. It's kind of hard to figure out, was I sensitive to these? Was I not sensitive to these? So it was a very, very hot topic of research just trying in, some number, about 10 years ago or so.
Do these galaxies behave differently than normal ones, or is that what you're trying to find out? Is that just a whole new...
Do they behave differently? This is going to get back to comets eventually.
Okay.
But so do these things behave differently? They, I think when people first started really looking at them, it was like, what's up with these? We don't really know what's going on. And then it really became clear that a lot of ways they're just on a continuum with the properties of normal galaxies. They're just slightly more extreme versions. So if you look at slightly lower masses or galaxies that are spinning a little bit faster on average for their mass, you kind of wind up with galaxies that look like this. And so it turns out that they actually fit relatively nicely into a lot of our understanding of the galaxy population. They're interesting because they're so different from normal galaxies that you can actually investigate. If you have some theory that works in normal galaxies, you should be able to extrapolate it down to these guys and figure out...
it's another way of testing your theory. In other words, if it extends to these different kinds of galaxies, you're on the right track.
Absolutely. Right. That's exactly right.
Okay.
Boy, you're a good science. That's
my job is to extrapolate the key thought.
Yes, good. Okay, so anyway, so that was kind of the stuff that I was working on at the time that the Sloan Digital Sky Survey really started going into production mode. And what the Sloan Digital Sky Survey is an ideal instrument in principle for trying to find these things because the way that it takes the data is through this process called drift scanning, which... So normally when you take a picture, you take your camera and you point it somewhere and you click it and there's your image. And that's the way that a lot of astronomical telescopes do. We just take our giant telescope, point it somewhere, there's a camera at the back end, and we do the equivalent of pushing the button and shutter opens, take an image, and the shutter closes.
Right.
So that's the typical way that you do things. Drift scanning is this very, very clever technique. I think it may have been pioneered, some of the earliest surveys with it were by Jim Gunn and Don Schneider, and Martin Schmidt. There may have been other people doing some of the early surveys, but the idea of drift scanning is that you point your telescope at some particular point in part of the sky, and then you just sit there. Now, normally when you take an astronomical observations, because the Earth is turning, it looks like the sky is moving overhead.
Right.
So in the same way, this is why things rise and set, is because the Earth is turning away from different parts of the sky. So what you normally do when you take your astronomical observation, if this is the sky over here, and then here's your telescope looking at it. As the sky moves, you track your telescope right along with it, so it always points at the same part of the sky. In drift scanning, what you do is you actually point the telescope in one direction, and then you just let the sky move, and then you do some funny stuff in your camera so that the camera keeps track of where the sky is pointing. It's a little complicated, but basically you've got this array of pixels, and then as the sky moves, you just move the image right along down the chip. And what this does, regardless of the method, which is a little complicated to explain in this format, it makes very, very smooth images with nice, smooth background properties. And so it's perfect for finding little bumps and things. So if you have something that's really smooth, you can find a little bump on it. So like on a bumpy sidewalk, you don't notice a small little crack, but if you have a smooth marble floor, you would notice that little crack. So likewise, if you have a bright sky, that your image of it is kind of wavy just because your camera wasn't that good.
Right.
So, but with this drift scanning, you get a really smooth, beautiful image. So it's perfect for seeing these low surface brightness galaxies.
Yeah, it's a contrast thing again.
Exactly. And so the better you know where your background is, the better contrast you have. So this was what I was trying to do at the time. And it turns out in practice it's a little hard to do with Sloan because there's a lot of, you're looking for these very low-level brightness things. There's a lot of stuff that can make low-level brightness things. So there's little glints off of neighboring stars. Sometimes if you have a big galaxy, just the outer little part of it will look sort of low surface brightness. And so if you're trying to do something, you have to do something highly automated if you're going to look through this huge volume of data. And so sometimes a lot of stuff you pick up would just be the outer part of some bigger normal galaxy.
Right.
So it wasn't going that well. So I was on this trip with a bunch of the American collaborators on this project. We all went to Japan to work with some of our Japanese colleagues there, and it was a wonderful trip. I loved Japan. We had one of the people I was traveling with, luckily, had been an exchange student there, and so he knew enough to help us avoid ordering the horse sashimi when we were in various restaurants, which I really appreciated. So anyway, so we were there working, and I was trying to get these algorithms going for, I'm going to automatically search for things that are big, that are kind of faint, and so I know that there can't be that much light there. And then I'm going to start looking at them. So pulled over some of these things, and we start looking at them, and it's like, oh, that's just a glint from a background star. Oh, that's just part of a background galaxy. Well, weren't really finding much. And then this thing comes up, I was like, what the heck is that? And it's like, that's a comet. So what it had picked up was the sort of soft, fuzzy tail of the comet. And it looked like a comet. Like, there wasn't anything. It's like if you ask a little kid to draw a comet, that's what it looked like. It had a little round head.
It's nice when that happens.
Yeah, no, it wasn't like... Nature usually tries to confuse you all the time. And this was something just like, short of just having a big blinking light saying comet, this was a comet.
There's a lot of amateur astronomers out there that are totally jealous of you.
I know. And the thing is, it's not what I do. I do galaxies. Galaxies are just... Yeah. We calculated this was like 13 trillion times closer than anything I had ever studied in my life. So,
now that's a size scale for you.
It is a really... Yes. So, and I study nearby galaxies. It's not even, so anyway, so this thing shows up that's clearly a comet. And then the question is this a comet that's actually known? Right? Because there's a lot of people doing all this good work finding comets. And so there's orbits, and there's the Minor Planet Center keeps track of where all these known comets are. And then we could figure out, based upon where this comet was on this particular date, is there some known comet there? And it had been a previously uncatalogued comet. Now, the thing that was kind of unusual about it is that normally, by the time when you find a comet, you're finding it right there. Here, we were finding it in data that was like a year old.
Right.
So we didn't know where the comet was now. We just knew where it was a year ago. And there was a real danger that the comet would be lost, because if we didn't know the orbit that it was on, because the sky is really big, a year later, it could be many, many different places. But what was lucky is that the way that with this drift scanning technique, so there's the sky, you can't see what my hands are doing.
Right, that's okay, but the other people will.
The other people can. And so then, as the telescope is pointing out and the sky is drifting overhead, the way the camera works is that it first scans over a little camera that's taking a picture through one color, and then another camera that's taking another picture in another color, and so on and so on. So you actually get sort of a series of... You get 5 different images that are separated by a couple of minutes from each one. And the center of the comet had slight changes in position in each of those. Just over the course of a couple of minutes, it was going fast enough that there was a measurable change.
See, and I've been studying calculus, so I know that from that set of data points, you could probably extrapolate.
Exactly. So then I had one of my co-workers at University of Washington, who happened to be a buddy of mine from college, Jean Monnier, had been working on one of these projects that was doing a lot of time variable observations of the night sky. And I'm like, Jean, we think we have this comet, it's going in this direction. Can you see, if you were to extrapolate this out in date, did any of your repeated observations land any place that might have intersected this at any time? So it's kind of a complicated problem, right? Because you've got to search through space and time. But Gene's smart, and so he was able to figure out, and he was able to recover observations of the comet that had been taken in the intervening time. And so with that, we were able to get a really precise orbit, and then we reported it to the Minor Planet Center, and then the amateurs were able to kind of come in and still track it and further refine the orbit. So it was a very backwards kind of way of doing it. So
yeah, but it's I kind of like that. I think a lot of people don't really understand how science gets done, and that for every really spectacular discovery, there's years of just poring over data.
I know, and a lot of I love the quote, and I think it was Asimov who said that, like, most science doesn't start with eureka, it starts with, well, that's fun.
Yeah, exactly, yeah.
And
it's been attributed to lots of different people, but I actually think it's Asimov.
Yeah, it sounds like Asimov.
Yeah.
It could have been Asimov's mom.
Yeah. He could have stolen it from someone else, we don't know.
Yeah. Yeah, so anyways, so since then, there's been a lot more work that's been done on comets in the Sloan Digital Sky Survey, so one of my colleagues, Željko Vezic, and a student at the University of Washington, Mike Solentoy, have been looking at other comets that have happened to fall in the Sloan Digital Sky Survey. So here they're not necessarily focusing only on discovering them, though they are working on that too, but there are also all these cataloged comets that happen to have paths that intersected the Sloan data at some particular time. And so they've been studying the colors of all of these things and trying to understand, do comets that come from certain places have different colors depending upon their origin in the solar system? Right. And they spend a lot of time mocking me because apparently Comet Dow-Canton is anomalous. that I have a funny color. I do not behave like other comets.
Well, there you go.
There we go. Right. So it is a peculiar comet because it was out near Jupiter in the original Discovery image, and it had a huge tail. Like, it's very unusual to have such a large tail so far out in the solar system. They usually don't develop large tails until they come into the inner solar system. And so it was speculated that maybe it was its first time in. It's also a bound comet, which means that it is going to come back again, but it's going to come back in 186,000 years, so it's not like the kids are going to see it. So.
But you have a comet named after you.
So this was the thing. It was like, are they going to name it, Comet SDSS 001? Right? Are they going to call it Comet Dow-Canton? Like, please.
Please let it be me.
I know.
Well, I know that there's like some sort of strange celestial object that's been nicknamed Buffy.
Right, yes.
For very similar reasons, because it just seems wacky and it doesn't seem to fit in with prevailing theory. And
Well, and I think that also some of that actually comes from that's work that Mike Brown's group is doing out of Caltech, where they're trying to find these very interesting outer solar system objects. So things like poor demoted Pluto.
Yeah.
And it's a relatively competitive field, and so normally a lot of astronomical objects are named after their coordinates on the sky.
Right.
And if you're in a relatively competitive field, maybe it's not a good idea to let people know exactly where you were looking on some given date. And there were actually some issues that came up in that particular project with competing groups not necessarily doing things that were quite so ethical. So some of those names are shorthand so that they can talk about a specific thing without really letting people know until they're really ready to introduce it to the public, right? Because you also, Buffy might have been something that they thought, hopefully, was going to be what they were interested in, but you don't want to release it until you actually really know and do the verification that, yes, I'm not going to say something that's going to look idiotic in retrospect.
Right. Well, here I thought it was all just to make it, cute names are better. They sell better with the public. In terms of PR, it's much better to not call it, SDSS number 0155 or whatever.
Scientists are much more interesting before we have to put things in press and whatnot.
So that's what we're doing right now. We're unfiltering. This is
pure
science, unfiltered.
We are taking off the filter. Well, if you look at very old articles in the astronomical literature, they're much more informal, colloquial. It's like, as we took the mule train to the top of the mountain and the sun was setting in the east, and they set in the west, so setting in the west. And so there are often these very poetic things, but now if you write a paper, if you put one slightly interesting adjective in there, like if you describe it as humongous rather than extremely large, one of your colleagues or the editor will cross out humongous and write large.
Yeah.
So it's
orders of magnitude larger.
Yeah, you can't say it's bazillions.
And ginormous will not be appearing in the scientific literature anytime soon.
I know, and it's so sad. I'm a fan of bazillion. I like bazillion.
Well, I understand why they want a certain professional tone to the papers and things, but some part of you has to mourn, the loss of color.
Yeah, I know, but that is something I think that blogging has actually brought back to it, is that you do get a better look at the fact that scientists are actually...
Right, it doesn't have to go in the paper, but you save that stuff for your blog post when you announce your paper.
No, I think that's true, and I think you had a recent blog post about sort of scientists and television,
Right.
and how some of these people or some of these shows are actually doing a pretty good job of kind of capturing the fact that a large fraction of what scientists are people who just like to figure stuff out,
Right.
and it's kind of fun to figure stuff out. Like you talk to kids love figuring stuff out. Like they feel really cool when they figure something out, and even adults do too.
Right, and I think that there's a reason that a lot of these science-themed shows are procedural dramas. They're solving crimes. They're, identifying, decaying corpses and things like this. It all becomes part of solving a puzzle. And I think there's something universally human and appealing about that beyond science. And it's getting back to the essence of science. In other words,
Right.
It's really all about human curiosity and exploring our world and solving puzzles. And I think that's something that everyone can agree and enjoy on. And I think that's one of the reasons why you're seeing this sudden uprise in the number of science-themed TV shows, which I think is very encouraging.
Oh, I love it. I mean, I'm a huge fan of CSI,
Yeah.
right? I mean, it's just incredibly fun. And things like Mythbusters and, I think what happens with science is that often you go to the end point where they show the person who really loves figuring stuff out about, the mating habits of stag beetles, which are incredibly interesting, actually. but they're not...
Grissom would agree.
Yeah, that's actually true. So there it's something where it's taken to being interested in something that somebody is not necessarily particularly interested in, but that act of being interested in something. Mm-hmm. There's some field of science or engineering where you would care about figuring it out. So maybe it's figuring out how to make your bridge stand up, mm-hmm. or, the water to filter correctly through the watershed, or...
Right.
It's all that same figuring stuff out.
And
very,
making
very
that
satisfying.
connection is what, I've always say is very, very important. I mean, the science itself is great and it's interesting, but what brings people in is this narrative of solving a puzzle. What puzzle are you trying to solve here?
No, it's incredibly fun. And these things like the comet, these things where they just kind of come out of left field, mm-hmm. or out near Jupiter, come out of now near Jupiter, it's like somebody just dumps a new puzzle on your lap, right? That all of a sudden, I thought I was putting together pieces to make the horse standing in the field, and it's like, what's this picture of the pig doing here in my puzzle? Huh. And then you've got to figure out the new thing. And that's really, a lot of the most interesting science is not the way they present it in standard kind of school curriculum. I have a hypothesis and I'm going to test my hypothesis. A lot of times, all of a sudden, you see something funny and it's like, oh, okay, I'm going to go off and try to figure that out. There is a lot of fabulous science that is done through a macabre thing. So things like what's happening with, the LHC and whatnot. There's no way you're going to do an endeavor like that without having a definite plan for moving forward. That's it.
Yeah.
But astronomy is a lot of the enterprises in astronomy tend to still be at a smaller stage. We're kind of growing into an era through things like the Sloan Digital Sky Survey, mm-hmm. Upcoming surveys like PanStar, the Large Synoptic Telescope. A lot of those things are taking us into a regime where it is going to be sort of more large systematic science. But astronomy is, I think, more so than a lot of the large physics collaborations. Even within these large projects, there's lots of avenues where somebody reasonably creative can find interesting, unexpected puzzles that nobody even knew was something to think about. Yeah.
Right. Getting back briefly to the TV shows, and then we'll move on. One of the things I really like about them is something that I think that Cosmic Variance is intended to do as a blog, is that the scientific characters in here, first of all, over and over again, they're repeating the mantra, follow the evidence. It's the evidence that counts. There are rules. There are standards. Mm-hmm. It's not enough to just follow your gut. You've actually got to be able to back it up with stuff. That is a great message to be sending out to people. And the second thing is it shows them as human beings. They make mistakes. They have human weakness. They fall in love. They have sex. They date. They break up. They have kids. This is something
and it sometimes affects how they think about their science.
And it sometimes affects their science, exactly. And they get called on it, and then they have to learn how to basically reconcile those two aspects of their personality. I see that a lot on Bones. I see it a lot on CSI. And I think people tend to have this idea that scientists, are just these dry,
brain in a box.
Yeah, brain in a box, exactly. It's very encouraging to me also that the public image of scientists will slowly start to change, and people realize that they're all shapes, all sizes, all colors, all genders. Both genders.
Yeah.
So, I'm still waiting to see a transsexual character who's a scientist, but.
you may already have, and if they're very good in passing, you don't know.
Exactly. Yes.
So that's. I was going somewhere. I don't know.
That's okay. I mean, I think that, obviously the big astronomy news, and I think you blogged briefly about it, is that the problems with Hubble, that basically they've had some the servicing mission has been tabled. Now, a lot of us just love Hubble just because
it's a
PR home run, really.
Regardless of the reason it's a PR home run, it really is. It's a really phenomenal facility, and it can do it can do things that you just cannot possibly do other places. So it's above the Earth's atmosphere, which does a number of things. So remember how I said the sky was bright because of all of those things in the atmosphere that were glowing after the sunset. Well, if you're above that, you don't get that glow. So the background is very, 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 space is much darker from the point of view that Hubble has.
So you get that higher contrast and more resolution.
You get much higher contrast. The other thing that happens is you don't have the atmosphere blurring everything, so there's a real problem trying to look at things from the ground, which is when you look at a really hot road, you're driving along the desert and you see that kind of...
That shimmering thing.
The atmosphere does that all the time. You notice it particularly on large scales in that scene, but if you look straight up, the twinkling of the stars is not the stars changing brightness, it's actually little bits of atmosphere sort of steering the image of the star around.
Oh, okay.
And so that actually makes the look of the twinkle. And that twinkle is bad because it's steering the star all over the place. And so if you're trying to take a picture of that star, which should, as most stars are far enough away that they should just look like tiny, tiny, almost infinitely small little points, you can't tell that. It looks like kind of a squash bug because the light is steered it around. Whereas if you go above the atmosphere, that twinkling doesn't happen and you get these super sharp images.
Right.
The other thing that you get from Hubble is that the Earth's atmosphere tends to preferentially absorb different wavelengths of light coming from both above and below as well. So one of the things that can't really penetrate the Earth's atmosphere is very far ultraviolet radiation. So even though you have to wear sunscreen to protect against UV light, at even either higher energies of ultraviolet radiation don't actually make it through the atmosphere in any kind of significant numbers. And there's a lot of very, very interesting science you can do with light that's emitted at those wavelengths, but you can't get it from the ground, so you have to go to a facility like Hubble in order to actually see it. So there's all these wonderful things about it. The problem at this point, the Hubble was launched in 1990. It's 18 years old.
Yeah.
Right? It's basically, a friend of mine described it, it's kind of like having an old VW bug in space. It's really, and it's not a large telescope. I mean, it's about 2.5 meters across, which, you could hug it practically if you were a really tall guy. You could, give the thing a hug. It's not that large. Some of at this point, before the most recent failure, I mean, the only instrument that was really working on it is one of the first cameras that launched on it, which this thing is it's called WIFPIC 2, the Wide Field Planetary Camera, and it's this tremendous workhorse for the system. But it's like a VW bug. I mean, I drove VW Beetles for years, and they get you where you're going, and they do. Sometimes that's all you're asking for. The problem is that they need a little bit of care and feeding, and so this is what this servicing mission was going to do, is that there's various little bits and drabs, same way in the VW bug, the heater stops working eventually, and you can't really roll the windows down, and reverse doesn't necessarily work in the transmission. On the Hubble right now, there's some of the gyroscopes that help point the telescope are gradually starting to wind down. The heat shield is showing some damage. You need to put something on to help kind of protect the innards of the telescope. And there are also the opportunity for sort of upgrading a lot of the instruments that are in there. So they have these wonderful new instruments that were scheduled to go on the telescope, and the mission to service the Hubble telescope was scheduled for mid-October, so right about now.
Right.
And I was so excited I was going to get to go. I've never been to a launch, and everybody says it's spectacular. I know. It's really nice. You get this little invitation from NASA with a picture of the space shuttle on it saying, you're invited. So that was a thrill, but it's going to be a thrill delayed at this point. So anyway, so it was scheduled. Oh, go ahead.
I was going to. Yeah, you're moving. Yeah.
Okay. So the launch was scheduled for October, and the astronauts have been training incredibly hard. I'll talk a little bit about that. And it's very complicated scheduling these launches because there's certain windows when it's okay to get to the Hubble and others where it's not actually optimal. They had to fight with hurricane season.
Yeah.
So that actually pushed the launch back. The launch was originally supposed to be in early September. but then various things have pushed it, including some lost time due to the hurricanes. It's an incredibly complicated mission because because they have to have a backup, so they have to have a rescue plan in place if something goes wrong with the shuttle and they don't think they can land it safely.
Right.
They have a backup shuttle on the pad to launch up that would then rescue the astronauts from the first space shuttle.
Okay.
So they have to coordinate actually multiple shuttles, which is
Yeah, it's kind of like air traffic control at O'Hare. Much smaller, with much bigger
space
things.
shuttles. Yeah. So anyway, so they have this mission scheduled where the astronauts go up. They use the Canadian robotic arm and they grab the space telescope, and then they do their what are called EVAs, their extravehicular
Stuff.
And then they go around and they take this thing out and they put on these fabulous new instruments. And this is something they've done. Previously, they've done 4 times, and it's kept the facility to be kind of top notch. I mean, like with a VW, you can just keep on replacing that engine, and that thing will just keep on going. And so they've really been. It's still a state-of-the-art telescope, but what's happened is had a series of some of these newer instruments have started to fail, and they have these backup wonderful instruments to put back in, and they have plans for fixing some of the really good instruments that are on there where a couple of the power supplies went bad.
So why did it fail? Why has it been delayed?
So the reason it's been delayed is that something else failed. Something else that was like really important. They weren't expecting it to fail, and it's called the Hubble Control. It's the Control Unit Science Data Formatter, and it's basically the thing that the instruments take a bunch of data, and then the telescope has to find a way to take that data and put it in chunks that they can then beam back down to Earth. Right? It's not like you can't plug in your core, your Ethernet cable.
Right.
Up into Hubble, and so they have to beam this down. And so it's that piece that takes the data from on board and shuffles it up and sends it back down to Earth that they need. That if that's not working, you can't really get the data down. Now, most everything, NASA's very good about building redundancy into systems,
Right.
so there's actually a side B that they can boot up. Now, it hasn't been turned on since launch, so it's been sitting up there for 18 years.
Freezing.
Well, but freezing is good,
Okay.
actually, right? I mean, freezing that's actually for electronics is not a bad thing. So there's a team right now that's analyzing, can we safely turn on these new electronics? How would we actually do this? Do we understand the way the first one failed? And is there anything that we can do in terms of our operation of the second to mitigate the chances that the side B would fail? Mm-hmm. But you can't, it's crazy to go up there, replace all these new instruments, and have the risk that this other unit is going to fail. So they really need to figure out how to do a repair on this thing as well. So thankfully it failed right before they went up there to fix it. Right? I mean, have you ever had the experience like you have an old car, you take it into the shop and they say, we need to put new struts on it and it's going to be $800.
Right, and they always find something wrong with the transmission right about after that.
Well, right. So the thing is you spend the $800 and then the next thing that happens is the engine drops out and you can't repair it.
Right.
And so this is something where luckily the engine dropped out beforehand, and so we can actually fix everything all at once.
So you will get to see a launch. It'll just be next year.
It's just going to be, it's probably going, there's a servicing mission that has to go up to the space station in February, and so it has to be after that one because of this problem of coordinating the multiple vehicles. But can I talk about how they actually train to do these repairs?
I do, because you mentioned something about a buoyancy laboratory, because we all know about the Vomit Comet, that whole zero-gravity plane. I mean, Stephen Hawking alone made it famous. But I don't think anybody really knows what this buoyancy lab is, because that sounds like a big bouncy castle to me.
No, it's actually a large swimming pool.
Oh.
Okay, so when they go up and they do these repair missions, the astronauts, right? They're wearing their big suits. They have, their little spacesuits. The gloves have actually gotten really good. They have these just absolutely beautiful articulated gloves, but it's not like wearing a pair of isotoners, right? They're not that easy to work with. And what they're doing are these incredibly complicated repairs. So some of the repairs that they were scheduled to do on 2 of the instruments, they have of order 150 screws that they have to undo and redo in order to do the repair.
Man, is that time-consuming in those big, bulky
in gloves, in space, right? And they have this really great, pardon me, my nose is really itchy. And they have this really clever system for doing this, where they actually have I think it's large. It's made of like anodized aluminum, and it has a bunch of different holes in it, and it's like a map of where the screws are. And they just take this and put it on the instrument, and then all they do is they just start sticking their little space screwdriver into all these little holes, and then the screws back out, but they stay in this little device. So this thing it looks like a little porcupine when it's done, because it's got 150 screws sticking out of it, and then they can move that out of the way, and so then when they put it back, they just have this thing with little screws in it. So it's a really clever solution to the problem of how do you get an astronaut to undo 150 screws in space wearing mittens. And but the thing is, all of this stuff, they have a limited amount of time that they can actually be in the EVA. It's very draining for the astronauts. They don't get a whole lot of sleep when they're up there, so, if they're out there too long, they're going to get tired and make mistakes, and you can't have that. So the astronauts, who are just unbelievable, they train for years before these servicing missions to make sure that they understand how the procedure goes, and they find this thing that people thought was going to work, it's actually really hard because I can't get my suit in, my arm doesn't go in that angle. And the place where they practice this is called the Neutral Buoyancy Lab, and it's the world's largest swimming pool. And
that is not what I was thinking you were going to say.
No, it's not. You thought I was going to say bouncy castle.
Well, I mean, it's buoyancy, but I guess that's water, yes, but I don't know. I guess I'm having a hard time picturing how they train in that, but go ahead. How do they breathe?
Yeah. Well, they're in spacesuits, right?
Oh.
So they're wearing their spacesuits, and some of the things that are different is, they're not weightless within the spacesuit, so that's a little bit harder. And there's drag when they're trying to move around in this tank of water, and so that's a little bit different than space. That's one of the things they can't really reproduce. But in this giant neutral buoyancy lab, they've got this space shuttle. They have the Hubble. They have a mock-up of what the Hubble looks like with where the instruments are, and then the astronauts go floating along in the water, and they have scuba divers down there who help support them, that provide that extra little thing to sort of neutralize the buoyancy. So they get a little bit of assist to make it a little bit more like they're weightless.
Okay.
And then they actually practice, taking the instrument out and installing it, and then taking this other thing here, and then moving it there, and then working the screws. And through practicing, they've really sped it up. So so one of the astronauts, who is a very, very experienced, he's been on previous Hubble missions before, is really just a terrific guy. And he's figured out how to do some of these repairs that they thought they were going to take 2 EVAs to do. They were going to do, I think, it's either 5 or 6 separate spacewalks in order to do the repair. And we weren't quite sure that they were going to be able to fit in all the, we've got this long to-do list of things that they wanted to repair. And we weren't quite sure that they were actually going to be able to get through them. And, they figured out ways to speed up all these processes and that they could fit them in. And so with more training, they should be able to fit in a repair of this communication units as well. So it's certainly possible that they will be able to do everything that they thought they were going to do, plus this new thing, but they can't do it without training, right? They need to train in their big tank. Apparently the hard thing in terms of the training in the tank is, at the other end of the swimming pool is a mock-up of the space station, and you can't have people practicing on the fake Hubble while there are other people practicing on the fake space station. And so they have this kind of coordination problem in terms of getting time in the tank.
I think they need another really big buoyancy lab or something.
You don't want 2 of these things.
How big are we talking about here? I mean, is it...
It's big enough to hold a model of the space station.
So it's kind of like what James Cameron did in Titanic, where he basically built a replica of the ship and then sunk it.
It's not unlike that. And we could see that ship. We used to drive down to Baja, Mexico, when I used to live in Los Angeles, and you could see the big ship kind of sitting there. I was like, what the heck is that? And then the movie came out and we understood.
Yeah, I don't think I was living here then. That would have been... I hope it's still there. I might want to drive down there.
I know. It's wonderful.
So scale alone, that's pretty interesting.
I know. I just love. I mean, I love astronauts. I mean, that's just. It's very. These people are putting their lives at risk, right? I mean, when they go up there, there's a 1 in 100 chance that they are not going to make it back down.
And we've seen that with the 2 Challenger disasters. And
that was the point. I used to want to be an astronaut until Challenger blew up. And it was like, no, I love it.
Suddenly, my enthusiasm has waned.
I know. I'm not a risk taker. But but these people are, and part of it is that they believe in the mission. That some of these people, they're scientists. Some of the people who are going to work on the surface ignition are actual astronomers, astrophysicists, and so they really believe in the value of what NASA is doing with these various programs, to the point that they are willing to spend years of effort training and then to risk their life. And so it's a triumph of human achievement. I find it very hard not to be moved.
Yeah, one of my all-time favorite movies is Apollo 13, because it really, I thought, captured that. I mean, I came out of that movie thinking, you know what, we went to space in a souped-up Buick.
Have you seen, like, some of those capsules? They're tiny. I mean, they're smaller than a VW.
They're tiny, and they're all beaten up. You can go to the National Air and Space Museum in Washington, D.C. and see some of these things, and these were, the computers were not nearly, microelectronics hadn't been invented yet. I mean,
no, it's amazing.
And
they were willing to do that.
And I'm sitting there thinking, man, I would have been terrified. It scared the hell out of me. Because, they are going out into the unknown, and they've done all these simulations and stuff, but as you just said, I mean, you can't account for everything. You've got to have these people who can really think on their feet and solve problems on the fly, and the movie really captured that. I mean, it was just, I get tears in my eyes every time I see it.
Yeah. Well, I think a lot of people have kind of lost touch with some of the wonder of this.
Yeah, we've lost that sense of wonder. It's become commonplace. Yeah,
and it still isn't, right? I mean, we've lost a couple of shuttles. We've lost a dozen astronauts. I mean, it's not routine, but it gets a little 30-second blurb on the news, and the fact that you can look up at the moon at night, and people have walked on that.
I know.
Like, see that thing out there? There are people, they were walking around on it.
According to some people, it was a hoax, but I
know you're gonna have to interview Bill Platt to talk about
I know.
That.
It's his favorite topic, and they did a marvelous episode of MythBusters, actually, kind of debunking that.
Oh, that's good.
They actually tried to fake the photographs, and it's like they built their little.
If I were gonna do a hoax, what would I do?
Yeah, and it just wasn't all that convincing, and they were dealing with much, much better technology, so.
Yeah.
The Mythbusters are wonderful. It's a great way of getting things across.
It's really. I mean, some of the stuff they do is kind of like a little ridiculous.
Well, I mean, look, it's about blowing.
The process is fun.
It's the process of discovery again, and it's at one level, it's about blowing crap up. But the people like to watch.
And I love that.
It's like pyrotechnics is a big crowd pleaser.
Yeah.
So. But, it's funny since I just mentioned the Air and Space Museum because, I grew up in Seattle, so I'm familiar with the Pacific.
Oh, I didn't know.
Yeah. So I lived on Queen Anne Hill in college and took a grad school class in English Lit at UW. So
no calculus involved.
No calculus involved whatsoever. So, and in retrospect, I can't believe I was allowed to get away with that. But I'm compensated.
I know it's acceptable to say, I don't do math, but it's not acceptable to say, I don't read.
Yeah, people really look at you funny if you don't read.
Yeah.
Like that whole grammar thing, I've just never been any good at that.
No, you can't be proud of it, but people are like almost proud sometimes that they...
Right, and part of that is a defense mechanism. I speak from personal experience.
Right. Yeah, right, no, exactly.
And because, it's a different language. It really is.
Yeah.
But one of the things, I used to always love the Pacific Science Center, and Sean and I just went to the Los Angeles Science Center a few weeks ago.
I've never been to the LA Science Center.
Yeah, it's very interesting. We actually went specifically to see the Body Worlds exhibit, which is,
Is this the one where they have, like, the actual
the flayed preserved bodies? Corpses, essentially.
Yeah. I couldn't really gear myself up for
that. I'm very morbid. I was a fan of Fragonard. He was this 17th century dude. He's a cousin of the painter Honoré Fragonard. But he was a vet and an embalmist. And what he basically did was he would take these bodies and practice with these various embalming techniques. But then because he sort of, I guess artistry kind of ran in the family, he really wasn't content to just make scientific specimens, so he would arrange them in these really bizarre tableaux.
Everybody needs a hobby.
Exactly. And they're really, there's like exposed bone and like, half desiccated skin that's been like tanned and is kind of stretched over the bones.
What's the record of all of this? Is it just a written record?
Oh, no, there's an actual Fragonard museum just outside Paris.
Oh, okay.
And they don't get a lot of foot traffic because it's not very well known. And a lot of people are like, Body Worlds was a huge smash, but I think there's a lot of people like you who are just kind of put off by it. And if,
Well,
if they're kind of,
I'm not. I just know my limits, right? I think I would find it fascinating, but there was just no point in my limited free time that it's like, I think I'm going to go do this thing that'll be interesting, but it's really going to squick me out.
Yeah, and a lot of people, if they think that Body Worlds is shocking, I mean, Fragonard, because he didn't have any of those moral, I mean, he was actually considered insane at one point and lost his job. But the museum itself is actually pretty interesting. It's like those, there's an odd medical museum in Philadelphia, I think.
Right, yeah.
So we...
Well, you're actually near one of my favorite museums, which is the Museum of Jurassic Technology.
We haven't been to that yet. I know, and I'm a huge, Anastasius, whatever his name is, the society, Cabinet of Curiosities dude.
Yes, right.
Because I love Cabinets of Curiosities. That's essentially what the Museum of Jurassic Technology is.
No, I mean, it's sort of a reduction to the essence of what a museum is, but based upon sort of fictitious worlds.
The other thing that's out here is the Museum of Tolerance, which is very interesting because one of the things that they walk you through this whole exhibit on, where you basically get pounded in how we all have our biases and this sort of thing. Mm-hmm. At the very end, you get to go through one of two doors, whether you were biased or unbiased. And of course, the trick is only the biased door will open. The other one is just a fake door. But
that's really subtle.
A friend of ours said that she was there one day, and there were literally, 3 or 4 Orthodox Jews banging on the unbiased door, demanding to be let in. And so, they clearly had not absorbed the message. So But the interesting thing about Body Worlds that I thought, and even that was very interesting, is the difference, I think, in attitudes towards these things, is that it became sort of there were all these weird public health announcements. Like they would show, a smoker's lung and a non-smoker's lung, and then there would be a little kiosk off to the side where you could leave your cigarettes and vow to quit. And then, of course, they went off on their anti-obesity kind of thing.
How were people reacting to that?
I don't know how other people were reacting to it, but I was kind of put off by it. I thought, just kind of let it be science. Don't sit there and preach at people. We get enough didacticism. And what I especially was interested in, because they actually did show a heavily obese body, and I've been in anatomy labs, so I've actually seen it's a little bit harder to open up someone who's got a lot of body fat just because you've got to dig through that much more. But the Body Worlds exhibit, I mean, you look at all these toned muscular bodies, and they're toned and muscular because all the fat's been stripped away. I mean, pretty much at that level, once you strip off all the layers of fat, we're the same.
Right.
And I kind of got a different message out of it than I think they meant to send.
That was.
So we have a little bit more time, and we'd want to talk a little bit about said science education, because I think that you had said that you're particularly happy with the Seattle curriculum. And I know you've got kids, so...
Yeah, the Seattle Public Schools are using this an NSF curriculum, an NSF-designed curriculum, which is, it's fabulous, mm-hmm. right? They went to the National Science Foundation, and the National Science Foundation has a curriculum that you can use. And they have kids doing, interesting experiments and investigations at a very, very young age. So in first grade they had them doing things with balls and trying to figure out which balls bounce better and which balls roll down hills faster. And they had them talk in advance about what they thought was actually going to be happening. So in terms of, was the heavier ball going to roll down faster than the light ball, and was the squishy ball going to bounce higher? It's never
too soon to get them started on that.
No, and so they went through the whole process, and the students kept really good records of, beforehand, this many people thought this ball was going to do that, and that was going to do that. And then they did repeated trials of putting the balls down the ramps to see which one rolled down faster, and then had them discuss afterwards, did they change their mind? And what was interesting is there was what the answer to that, what actually happens in the real world is not intuitive. It's not what somebody would just think automatically. You naturally tend to think that, the heavier ball is going to go faster, but that doesn't really work that way most of the time.
We all learn that, but we all tend to forget it. I mean, I've actually seen physics teachers momentarily forget that.
Oh, yeah, no, it's very deeply ingrained. And so then afterwards, even after they've collected all this evidence, there was still just a few die-hard kids in the class.
No, that can't be right.
It
goes against nature.
Right, exactly. But they just couldn't let go of that. Mm-hmm. And it was, but overall, it was really reproducing a lot of the process of what happens in science, right? That you have some idea about how something might work, and that you can go out and you can test it, and that the tests are not perfect, and then have them discuss, well, why might the test, and the students were like, well, maybe we didn't release the balls at the same time, it was kind of hard to see, you had the right angle about which ball got down to the bottom first, so they thought about their experiment. They did multiple trials to kind of get around some of that, and then afterwards they discussed, how did things change. I was really impressed. I mean, it was a pretty good recreation of some of the processes that you actually do. And what's, I think, nice about it, it's that whole thing about what's wonderful about science is helping people understand that this stuff is not magic, right? That you can actually do things to help you understand these things and figure stuff out. It's amazing what people have.
Right. And it's a very important aspect, I think, because if you just have them learning from the textbooks and from lectures and memorizing facts, it's not that those aren't important. It's that unless you're actually doing the experiments, you're kind of taking it on faith. And I think one of the problems with that education, we see that, widespread. People are saying, well, I just don't happen to believe that's true. I believe this. And for some reason, we have failed to get across that it's not about belief. That in fact, these things that we're teaching you have been tested over and over again, and now we're going to prove it to you. And I think it's important to have that aspect.
Right, but often, though, the way that some of this stuff is presented, it's also presented on faith,
yeah,
right?
They say,
I believe this, and then it's like, scientists say the opposite.
So they're asking
and so then you're just supposed to take that on faith.
Right.
And without a real understanding of the process of science, and that, scientists actually really have pretty good reason for saying that.
Right. I mean, I think you cannot just appeal to the authority of scientists. You've actually got to prove that there's a reason why scientists say this.
Right, and I think that's part of, the more people you have sort of understanding what this process is like.
Because otherwise, people just say, well, the Bible says this, and why are scientists, more important than the Bible? I mean, for some people that's an actual argument.
Yeah.
So.
No, I mean, it's just, I just find science so fun. I mean, I love my job. I'm very, very happy to be doing what I'm doing, and it's I'm always just baffled that other people just didn't have that same experience. I was very fortunate.
It's funny because even though I was a humanities person, I always really liked science. I just, there were a whole lot of factors in high school, social and all these various things. Not any one thing, a whole combination of factors that kind of like drove me out of it. And not necessarily for a bad thing, because I think that, my strength really was words and verbiage. But
and what you're doing is wonderful.
Right.
I mean, you really are doing a fabulous job of translating some of this stuff.
But I also don't think I don't think I'm really all that extraordinary. I actually think that a lot of people could, a lot of people do share an interest, in just science. And for some reason, we've kind of lost that. I mean, we were at the Science Museum, and it was on a weekend, and it was a really sunny day. You'd think people would be out at the beach because it is California, and it was packed.
That's great.
A lot of people are really, really interested.
Well, there's people who are watching this right now who, they could have been spending a perfectly good hour doing, doing something else. And so that's one of the fun things about blogging, actually, is that we get lots of emails and comments from people who are they're just into it, and they may be lawyers or, they may work in factories, but they're really, really interested in this stuff. And it's nice to be able to have some medium where those two spheres can interact, because so much of society winds up just being segregated by class and by interest. And I actually find blogging is one of the ways that, at least, with the subset of people who have computers and have discovered the blogging universe, it's some way that we can all kind of get together and have some of these discussions, and that's really
right. And I think
really
that's going to continue. I mean, blogging is still a relatively new phenomenon. 10 years ago, almost no one blogged.
Yeah.
So,
but people have been holding forth for thousands
of years.
Oh yes,
people have been holding forth. You can't keep us from holding forth. We will always hold forth.
Yeah.
To me, this gets back to again. We're also seeing, the fascination in the rise of science-themed shows. And in this recent blog post that I wrote, I think I closed with talking about House, because there's a new show called The Mentalist, where essentially this is the first time you've seen an overtly skeptical viewpoint, unless you don't count House, who I think is he's the character that made The Mentalist possible. Yeah. But in there, I think he has this exchange with a musician which I think really captures the dichotomy there, where the magician is basically saying, people come to my shows because they want a sense of wonder. They don't want to know the secret. They don't want to know how it works, you know. That's where the magic is, in that sense of wonder. And House responds, basically, you know, if the wonder's gone when the facts are known, then there never was any real wonder. And that's in line with what I've always said, which is that it's, you know, and House also said it's way cooler to know. But essentially, you know, something that seems like magic and kind of cool is even cooler.
It's even cooler
when you find out why it happens and that there's a reason for it and it's not magic. And I like you, I mean, I don't understand why that isn't cool. That's totally awesome.
Well, I mean, you know, sometimes we haven't done as good a job of explaining that as possible. And there haven't been as many mediums to share that with people. And because it does take a certain amount of informality to help to have that discussion. I mean, you know, Cosmos and, you know, Nova Specials and whatnot do some good job of that, but but it's a more limited audience.
Well, and also in that, I mean, it's a lecture mode, and that's fine, and these are great communicators, but more and more, I think we need more actual interactions. People don't know physicists; they don't interact with them in their.
Well, there's not that many of them, right? So
I know, and I forget that because now, of course,
you spend all your time, right?
I mean, we Sean and I had dinner earlier this year. It was a kind of a benefit dinner with some people who were not scientists, and one of the women said, I mean, how often do you get to have dinner with like 2 or 3 scientists? And I had the freaking time, you know?
Oh, my God.
And it occurred to me that my reality is no longer, you know, what it used to be, you know, for that reason.
Yeah.
So... But I don't know how you do that. But basically, once people start, you know, meet a scientist and talk to them and hang out with them, you know,
it really demystifies.
It demystifies it a lot, and it generally has a positive impression, unless.
Yeah, no, there needs to be like a dating service for people from the general. Like, you know, I married a non-scientist, and you know, the first time he met a bunch of my sort of friend, coworker people, he's like, "Oh, astronomers are so eccentric, you know, you just have never seen."
Well, and of course the astronomers don't realize they're eccentric, or they don't think of themselves.
No, because we're totally, you know, within, you know, a group of scientists within their own culture.
It's not eccentric at all.
No, they redefine their local normal.
This is actually a funny story because Sean and I had dinner a while back with some of my fellow college English majors. I've stayed friends with them over the years and introduced them to Sean, and we all went out to dinner in downtown Seattle at Wild Ginger. And came time for the check, and Sean, of course, just glanced at it and said, okay, everybody owes this much, and they all just stared at him. It's like, that was awesome! You like, added stuff up in your head, because they were all dreading having to, like, figure out the tip and do all this sort of thing, and then Sean just kind of waltzed in there with his mathy skills and solved the problem, and they were eternally grateful and very impressed, because it just, you know, I mean, again, it's a big problem. I mean, figuring out the tip should not fill us with trepidation. You know?
Yeah, that's.
But it was a funny story. You know, again, the clash of cultures.
Yeah.
So.
Okay, well, are we out
I
of
think
time?
we're almost out of time here.
So.
Yeah, my.
Well, it's been a pleasure talking to you, Jennifer. It's nice to actually finally almost.
I know we were up in Seattle for a family thing, and you unfortunately were out of town.
Gone.
But I'm up there a lot, so.
Okay, well, we'll have to get together.
Okay, great. I will talk to you later.
Okay, hey, thanks
All
a lot.
right, bye.
Bye-bye.